talk about parallel program design. And so now we're talking about the computation side of things. And of course, when you start, somebody says, write a sorting program to do sorting on 5 computers or n computers. Where do you begin? Right? You might have the underlying sequential algorithm in mind. Based on that, how do you take that and say, now have a parallel version of it, run it in parallel? Okay. And so sometimes you can just inspect. You can say, here is the sequential version, and these are the parts that can be done in parallel. Right. So if you're ray tracing some scene, then you know that every ray is independent of each other, and hence it can be computed in parallel with the other rays. Okay. So there would be automatic parallelism that the underlying algorithm will exhibit. Okay, and you can take advantage of it. You can simply say all those things that can be done in parallel, go do them in parallel. Okay, but it's easier said than done. So the places to look for would be, are there similar things being done on various pieces of data? Okay, for example, matrix multiplication. You're repeating the same thing to generate each element of the final matrix product. Okay, so that suggests that there are lots of things that are happening in parallel. Again, you can see, are there lots of input data that are being processed one after the other? Or are there lots of output data that are being generated one after the other? Or is there some intermediate data where you're taking input, doing some processing and generating a bunch of data, and then processing each one? So this input-output can be happening at any stage of your algorithm. Okay. There would also be functional decomposition. For example, you see that some function f that you need to compute is compute g1, compute g2, compute g3, compute some number of functions on x, same piece of data, and then compute some h on all of those intermediate results. So h cannot be parallelized, but g1, g2, g3 can probably be done in parallel. Similarly, recursion can often give you some hints about parallelization. Right? For example, this Fibonacci recursion relation says fn is the same as fn minus 1 plus fn minus 2. So that means you can do fn by doing fn plus 1, fn minus 1 and fn minus 2, and then adding them.
But for example, even in this case, how will you compute fn minus 1? It itself will depend on fn minus 2.
This is just a starting point. Right? It says where to begin. In a default way, you would say, I'll do fn minus 1 and fn minus 2, and they will be added together. Right? Fn minus 1 in turn will do fn minus 2 and 3. Fn minus 2 will in turn will do fn minus 2 and 3. And then these are all parallel pieces of work, except you're repeating lots of work. Right? So then there is a determination to be made about what can be independently computed where needed, what has or should be taken from somewhere else which has already computed this result. And so that trade-off is a very real trade-off that you're going to have to investigate. And basically you have to look for that kind of, so in this case, once you look deeper into the recursion, you see that there is dependence. Right? Either you separate that dependence by replicating computation, or you incur the cost of that dependence by doing it once and then having 2 people wait for the result, or some k people wait for the result. Okay, and the other example for this dependence is when you say composition of functions. When your code kind of looks like compute g on your input, and then on g compute h, and that's the result, right? So g has to be done, then h has to be done. So this kind of dependence has to be investigated, and then figure out, either break the dependence or design your parallel program to respect that dependence. Right? You have to do the first thing then you have to do the second thing. And as a general principle, you would want to take a serial program, and if you really are interested only in saying, I've got to run it 10 times faster than it was running, or 100 times faster than it was running, then you will see there are lots of small things that can be parallelized that look like lots of independent things happening together. There's this big chunk of code, or maybe physically a small set of instructions where most of the time is being spent. Right? So when you profile, you say that 90% of the time is being spent here, 10% in this rest of the program. And then of course you'll want to parallelize that 90%, right? 10% may be very well parallelizable, but it won't get you anything. Remember Randolph's law. So you'll profile your code, see the parts that are the most expensive, and then focus your parallelization on that segment, on those sections, okay? Similarly, the same issue will apply when your sequential code is organized as do this, then do that, then do that on sequence of things. And then you'll see that there is some stage of the pipeline which may be a bottleneck, because that takes much longer to do than all the other stages that pass data on. So the slowest stage of the pipeline will determine the speed, so you'll take the slowest stage and say, do just that part in parallel. You break that into parts that can be done in parallel and then do them, okay? But all of that is starting with a sequential algorithm and looking for places which you should parallelize. And how we'll talk about, but just basically saying, see where parallelism may be available and is useful to do. But oftentimes, at least half the time, you'll realize that the sequential algorithm is not the best algorithm to run in a parallel environment. Okay, so then you'll say, can I restructure this entire algorithm in a way that you break these dependencies, you have lots of independent things to do, which can be done in parallel. Okay, so then the algorithmic side of the design will have to be investigated. Is this sequential algorithm what you want to parallelize, or there are some adjustments that you should be doing? And typically in some cases, the parallel algorithms you'll see is just completely different from the sequential one. But in many cases, they are just small tunings that you do here and there, and it suddenly becomes parallel. Okay. So once we have determined that here is the section that we need to parallelize, it's slow and needs to be done in parallel. What are the issues that you need to look at? Dependency is one we talked about. Right? This part of the computation uses the result of that part of the computation, which means that part has to be done first. You're going to ultimately be doing two things. Right? You're going to say, I've got this computation to do, pool of computation things, and I'm going to decompose it into kind of tasks. Okay. Task is, imagine, essentially a capsule of computation. And I want to decompose the entire computation into tasks in a way that the dependence among tasks is small, right? And dependence can be in terms of you needing some data that I produce along the way, right? Which is called data dependence, meaning that I produce a piece of data that I'm going to give to you, and then you continue and I'll continue. And the other is task dependence, which says that I cannot begin this task until you are finished. Okay. You finish, and then I start this other task.
It's the same thing, right? I mean,
no.
How can there be task dependence without data dependence?
No, data dependence is on a specific piece of data. Right? It says that I am producing lots of things, right? And I'm going to give you one of those things. So that is the dependence on one piece of data. Right? And the other is I am doing lots of computation and then I am done. And only when I am done have I produced something that you will be using? Right? It is typically data. You're waiting for me because you need something that I am doing. Right? I'm producing. And but I am not going to be producing that until I'm done. Versus I keep producing a sequence of things and you keep using them. Right? So one is listed as a task dependence graph, where you say that task depends on this task and can be done only after that task is done. And the other is task interaction graph, which says that I interact with the other task. Dependency is typically one way, right? I depend on you. You are done, then I begin. Interaction is two way. I give you some data, I get some data back, I give you some more data, I get some more data back. So there is no one-way relationship that we are establishing, that you begin after I like a function call, for example.
And for the task dependence, it's like we sort the data first in this assignment, for example, and then we kind of find results. So the task is
that in this case that would be the dependent.
that's task dependence, not data.
There is data dependence also there, but that is
That can be
that you would call task dependence, right? Task dependence is related to data dependence, but we typically think of two separate graphs because they have two different kinds of information. One is the task dependence graph and the other is the task interaction graph. The other is, so you've got to design the task. You have to say, I want big tasks, small tasks. I want to have these tasks depend on each other or not. So why is big task or small task important? So there is some relationship between the task that will be scheduled on the computer, right? So if you have lots of tasks, then you have lots of things to schedule. But even if you ignore the scheduling time, say as soon as you're done, I'm just going to be able to schedule the next task. Then there are some issues that you would expect among bigger tasks versus smaller tasks.
Starvation.
Exactly how?
Small task which would say completing X time waits for a task to take some time.
Yeah, that's one issue, which is the difference in the size of the tasks. But if I have lots of small tasks, they're all small. Right? So nobody is waiting for something that's big. They're all small versus, so I take the computation, say ray tracing example again. I've got 1 million pixels to produce, that's 1 million rays. I take one task, which is one ray. And ray tracing is a bad example because there is no dependence among tasks. But an example of granularity is still here. So I can say one task is one ray, and I've got a million of them. Or I can say one task is one square block on the screen, and I've got 100 of them. Each task has more to do. It's perfectly balanced in both cases. Every task is the same size. But in one case, I've got lots of very small tasks. In one case, I have got small number of bigger tasks. So what would you expect in general?
So the scheduling time is not a problem, switching time is not a problem.
There will be a problem, but they are probably less of a problem than other issues that you would have to consider when breaking your computation into these tasks.
Scheduling is not the context which is not an issue. Then should be equivalent because the processors and virtual processors become equivalent, right? If there is the
It would be equivalent if there is no dependence.
If there is dependence, then the graph, the dependence graph becomes very huge in the case of smartphone.
As a result of which, you have to respect all these dependencies, right? Which means that if the scheduling of lots of things will depend on lots of other things. And so you'll just not be able to schedule them in the way you might want to. You have too many constraints. And so why not just use very large tasks?
for example,
What is
like
it?
pipelining thing, right? Because if you're very big task, and it's like a pipeline, and if it is kind of so.
Then this case will come into picture. The waiting time will increase. Because there's huge task and a small task.
No, but now I've got all huge tasks. Typically, the utilization goes down. I've got a huge task, and for some reason, this task has to wait for something else because there is a task interaction graph which says you need to produce some data before I can use it.
And that is also a big task.
Right? That's also a big task. And so I'll have potential of lots of idle time.
Similarly, if I'm waiting for some hard disk, means waiting for some memory on the hard disk, then other tasks can be scheduled on this CPU.
Exactly. If I have lots of tasks, then I have lots of things that can be scheduled in this downtime. When I am busy, somebody else is ready to run. But if I've got only one task, then either I'm running or I'm not. Right? And so you've got to figure out how to size the tasks, and the dependence of that is on how well the communication task interaction is going to depend on how you size the tasks. Dependence will also depend, because once you take lots of small tasks and group them into one big task, then internally it can just do them in whatever order it sees. It doesn't have to worry about somebody waiting for somebody else to give it some data. Okay? It's being done in a sequential sense. Communication automatically comes with synchronization. Right? Sometimes communication always requires some kind of synchronization at some point. Sometimes you need synchronization even when you're not communicating explicitly data. I want to have done something before I want you to do something else. Right? Barriers you have seen, for example, or locks, where only one of us should be taking the next item from the queue, for example. Okay, where we are not sharing data directly. We are still sharing a resource, but we are not directly communicating. We are not producing something and saying, here you do that. We are simply synchronizing because we want some global consistency to be retained. Okay, and then load balancing. Once I have determined that these are the tasks, that's a good distribution because it reduces communication, it reduces synchronization. Then how do I make sure that these tasks keep the processors busy? Okay, so that's the last important thing to consider. So we'll take all those 4 issues one after another. In communication, again, the reason that you would be reducing this communication is not just that there is synchronization associated with the task, associated with the communication, but also that communication itself has overhead. Right? There is somebody writing data into some buffer, and potentially and typically several levels of buffer. I write into my software interface API. That API writes into the network layer. Network layer writes some data onto the physical layer. And so there is several copies typically involved. And so all of this copying, packaging, transmission has an overhead. Even if there was no synchronization needed. I can send anytime I wanted, and they could receive in the background. Okay. The other is the issue of how much data can I send. There is fixed amount of channel bandwidth available. And so if I have taken a task that communicates a lot with other tasks, then the bandwidth is going to become an issue. Latency is another issue where if I must communicate something and wait for the result in response to that communication, then I must wait until this data has gone all the way there, been accepted, been looked at, been answered, and then the answer has come back all the way here. Okay, so you'll take a close look at whether what kind of bandwidth is available and what kind of communication you're going to require. Is it something that depends on latency, right? For example, if you're simply writing something to memory, that's communication. And that is typically latency driven communication, right? If you read something from memory, you send a request to memory saying, I want that piece of data. That request will be responded by that piece of data, and only then you can do the next step. Okay? And so you're going to have to find ways to hide this latency typically in any program, where you either run lots of threads, just like we were just talking about. We have lots of tasks, and when I am waiting for this thing to do its round trip, somebody else may be employing the CPU. Okay. The other is prefetching. Right? I send this request before I actually am going to need it. Right? So I anticipate that few steps from now I might need this piece of data, and I send that request off. And then a few steps later, when I do need that piece of data, hopefully that response has come back. So those are two general ways in which you hide latency. And it's prefetching directly is not exactly what a program directly controls. It is more like pipelining. Let's say, for example, I want to multiply one row of a matrix by one column of a matrix. I know that I am going to go through the entire row and the entire column. Right? So I read a part of the row, and I read chunks of the row, and while I read, I have read it, meaning I put it in some local variable, and that means all those requests have been issued. For the second chunk, I am processing the first chunk, okay, because they are stored in some local variable. So instead of having a variable which reads one from here, one from there, multiplies it, you have two variables which reads one from here, one from there, again read one from the next one from here and the next one from there, and then you go and multiply the first one you had read. Okay, so you read in, and two is just an illustration. You typically do it in larger groups, where you would read 10 or 16 or 32 or something like that, and then you read another 32, and then you process the first 32. So your code is itself structured in a pipeline fashion, so that you are reading and then doing something else, and then working on the variable that you just read. Okay.
Did you mention this explicitly in a code, or this compiler generates?
No, compiler will have no way of knowing this.
Compiler would actually reorder this.
Compiler can reorder this. The compiler reordering is a gray area, right? You can either turn off reordering, which is typically not a good idea, or when compiler will reorder only when it sees that there is some need for reordering, right? When you typically do this pipelining, compiler has no motivation to reorder that or reorder back to the original for you, because there is nothing to gain. So in this case, compiler wouldn't typically reorder.
In case of parallelizing, is the way we parallelize depending on the software which handles it? Because one may give a particular construct to do something and the other may not give.
Absolutely.
So then we have to, our algorithm has to be specific to how we use OpenAPI.
So you try to keep it as disjoint as possible, right? So there are some high-level things that you do, which would be somewhat API architecture independent, but you're going to get the most mileage when you take that into account.
Depending on the package.
Depending on the package as well as the hardware.
So there's going to be a problem in portability.
There is an issue, right? So the state of the art in parallel programming or parallel architecture, as well as the standard compiler and programming and interface and all those things, is not consistent enough across architectures. that portability is, let me say, much more of an issue than in sequential programming. In sequential programming also there are issues. Not everything that you do on a Linux will apply on Windows, or for that matter a Mac. Okay. So in terms of the communication, you have to look at whether you want to do synchronous, you need to do synchronous communication where we are sending data and that guy is receiving it, and only when that guy has received it, acknowledge the receipt, whether or not a response is coming back, can I proceed? These are blocking. In fact, we'll see very soon when we look at MPI. There are blocking calls where I say send, and when the send returns, I'm guaranteed that receive has been done on the other side. Versus I send and then immediately it returns and I don't know when the receive is going to happen. Okay, so that's the asynchronous kind of communication. The other axis on this design space is whether you're going to be doing point-to-point or pair-to-pair communication as well as synchronization versus group. You can multicast versus individually send, or multicast is not always available, but broadcast maybe. And similarly, in the synchronization space also, either you are synchronizing with a specific processor by sending a message or by locking a shared variable that you and that specific processor share, or something like barrier, which says that all of these group of processors together are being synchronized in a common way. Okay. Talking about synchronization, typical things that you would be using would be barrier. Barrier are relatively expensive. There's also a variant of barrier that's called a memory barrier that some architectures support, where you basically say that all the operations to that section of the memory has been completed. It has more to do with the memory consistency issues that we talked about before any other memory operation that happens after that barrier. Okay. And they tend to be a bit more lightweight than compute barrier. Lock semaphores you probably have seen in OS courses as well. Communication is another way to synchronize. Right? When I return from send and I know that the receiver has received it, some synchronization has happened. I can assume that something everything that was happening before the receive has been done. We'll also talk about synchronization that doesn't use locks. It's called lock-free, or there is also a looser variant called wait-free synchronization, which can be efficient in many situations, not always blindly efficient. But when you're thinking of what synchronization method to use, where to apply the synchronization, it's generally a good idea to begin by being conservative. Okay, because synchronization is the single largest source of error that parallel programs have. And so it's better to, if you think synchronization may be needed, you synchronize, and then once you have figured out that things are correct, then you may do a second pass and worry about performance. Okay, because if you get stuck with the wrong synchronization, a bug which is because of a synchronization, these tend to be extremely hard to trace, and you might want, or you might have designed it to be great in terms of performance, but you'll never be able to run it if you don't find that bug. So it's better simply to start by, at least as a beginning parallel programmer, start by being conservative, get it right, and then try to remove synchronization where you might think it.
What is lock-free?
You don't lock shared variable.
So you assume the access is such way that
Yes.
the updates are nowhere going to lie. Very important.
We'll talk about it. later on. Right now, you just assume locked synchronization. Right? So anytime, and in fact, as a general rule, basically stick with locks, unless you're sure that your program needs something else. Whenever you need synchronization, your first thing you should think is locks, okay? Because they're reasonably efficient and generally would fit all kinds of situations. And so, if you're not sure, then use locks, and then in a second pass, you figure out what it is exactly that you need. Okay, let me stop here so that we can start the next section. Are there any questions on? And again, we are talking about very generic stuff right now, so it shouldn't be too hard to follow.
So this is related to the BSP model, which
No, not this. This is just no. This is for all models, whatever your underlying programming model may be. These rules apply equally well. Right? Whichever model may be, you have to break it into tasks. You have to take these tasks and then run it somewhere. Right? So
in OpenMP, we have not basically done this exercise of dividing the code into tasks.
you have, even if
But it
you.
was more related to finding the parallelism in the loop instead of.
So that is task. Right? A task is not necessarily breaking the entire program into tasks. Right? You'll say, I've got this. So what I said was, you start with this sequential program, and this is a section that is hard because it's taking 90% of your time. So you'll leave all of that potentially sequential, because there isn't much to gain in the effort that you'll put in that section. Right? So all of that is kind of untasked. Right? It's just there being run sequentially on one of your processors, and there's this section which either because your dependency can only begin after all of that has done, or maybe can be preemptively scheduled early. Okay. Now that's the section that you're going to think about how you take that section and break it into independent units, which may interact with each other, but these are still tasks. Okay. So when you're doing that for a loop, that's what you're doing. You're saying that is sequential, this may be sequential, but let's figure out how to do this section in parallel. Okay. All right. For load balancing, we'll go one level deeper in for each of these slides very soon. But at a high level, your job for load balancing is to keep the load balanced, right? Keep every processor occupied all the time. If the tasks are similar sized, makes load balancing a little bit easier. But typically you will not be able to make tasks similar size, and it's not even necessary for load balancing to require the tasks be the same size. Right? You can balance load even when the tasks are dissimilar in size. You can balance load when even the machines are dissimilar in size. Right? You need not have all the processors having exactly the same amount of power. Right? In general, you can think of it as some variant of an NP-complete problem, right? You've got lots of these tasks that you have figured out, and you have to figure out how to allocate them to processors so that the processors are kept busy. Okay, knapsack problem, exactly. So that basically is a variant of a knapsack problem. Okay, and moreover, not that knapsack problem is easy to solve, that you may not even know what the task size is, how long it's going to take to run. Right? To have knapsack, you've got to know what size each thing is. Right? Task size may vary dynamically. So you've got to keep the load balanced dynamically. As the task keeps taking more time, you have to figure out what to do where the processor has become idle because that task is finished. Right? And again, at a high level, the trick is to keep enough tasks in hand so that if somebody has become idle, you give another task to him. I think we more or less talked about all that is here. In terms of granularity, basically the trade-off is between fine-grained as well as coarse-grained parallelism. Right? It's fine-grained will typically be able to keep idling processors down as much as possible. But dependencies and the amount of interaction can go up. The other thing, and so what's listed here is also in fact something that you use as a metric, which is the amount of computation divided by the amount of communication, right? Or the time spent in communication per unit time of computation, which is one of the metrics that, if you recall, the BSP model used. Okay, so when you have small tasks, then you typically have that thing go down. Right? You do a small amount of computation and some communication because there is much more of communication happening. And in large tasks, you can, even if all of that data still is being shared, by ensuring that it is shared locally, as well as ensuring that it's somehow batched, right? You can send lots of data together rather than independently. You can reduce the communication overhead overall for large tasks. Okay. And again, there is no one answer for whether you should be using a small or a large task, right? It typically is you want to keep it as large as possible, but the problem with large is that load balancing is going to be an issue, and so you've got to have enough of them on hand. Right? So you start with big, and you keep reducing until you've got enough. That's one rule of the thumb. The decomposition of tasks. One is domain decomposition, what we were talking about earlier. Take input, take output, or input out of some intermediate stage, and you simply take that and divide it equally or non-equally, doesn't matter. You just divide it. Right? Typically, you would divide it equally, make large number of divisions so that you have more tasks that can be used to fill up an idle processor. Functional decomposition is, again, we've looked at examples. If it's clear from the task that you're doing function 1 and function 2 and function 3, then and they can be done in parallel, then you do them in parallel. So this is functional decomposition. And then you typically try to have as many functions as you can, and enough functions so that once one function finishes and there is empty processor cycle somewhere, and you have some function waiting to be computed. Okay. Pipeline decomposition is another example where the underlying algorithm automatically says you've got to do this and then that, and then there's a sequence of data that goes through the same.
This domain decomposition and function are like parallel to SIMD, MIMD, because domain.
You can kind of think of it that way, but not strictly. Okay, domain, just because you're decomposing domain doesn't necessarily mean that you're doing the same thing on every piece of data. It's just you look at the structure of the program and it says that I've got these sequences of data items to process. How to process each data item is not known. Right? It can be different.
Is pipeline different from functional? Is it like pipeline
Is more a type of function. Right? So in some sense, there's just two kinds: data decomposition and function decomposition. And then these are, you can see pipeline typically in function, but you can see that in data decomposition also, because you're basically saying send this data to that and then that data to that. So maybe this slide should be structured slightly differently. Domain and functional decompositions are the two categories, and then all those different are techniques, how you might do domain decomposition or functional decomposition. Recursive decomposition will typically again come from some kind of a recursively provided algorithm, like divide and conquer, for example. You would typically not want your entire parallel program to be recursive, right? Because recursive is supposed to have an overhead with sequential also. With parallel, it only goes up, okay, because you have to decompose it so many times. But just because the original function is defined recursively doesn't mean that you have to actually follow the same recursive algorithm in parallel also. Although you can do the same static recursion. Okay. This recursion would have said that gets broken into these two, which gets broken into these four, which gets broken into these 16. Say, okay, that means I've got those 16 that will get subdivided. Okay, especially if it is static recursion. Sometimes recursion can be dynamic, in which case you do this recursion for a few levels, but at some point you stop following the recursive algorithm function, and you've got, at the point you've got enough tasks. So now the remaining thing, you don't divide and conquer, or you do divide and conquer, but you don't decompose that divide and conquer. Okay. And then there are more esoteric kinds of decomposition. One is exploratory decomposition, which is typically in a search type algorithm where, or optimization type algorithm where I'm looking for a solution and I do random walks. And so in a sequential case, you will say do that, then do that, then do that, and then evaluate something. Okay, and here you can say do these 5 things in parallel, or do these 10 things in parallel, and then evaluate something, and then do these next. From there you explore more. Okay, and so again it's automatically coming from the style of the original sequential algorithm itself. Speculative decomposition is where it's typically in the dynamic setting where the tasks, you don't know what tasks there will be. Tasks get generated. When you do something, new task gets generated. And you speculatively decide that in the beginning I have nothing. I start and I'll do, imagine recursion. I'll do something and then that will generate 3 more tasks. Then I'll take this task and expand it further, which will generate 5 more tasks. I don't know that, but that's what happened. Then I'll take the second task, that will generate 10 more tasks. The third task will generate 2 more tasks. So I might say, instead of my running all these tasks and determining how many subtasks it generates, let me generate, if I can, all the subtasks that might have been generated, run them, and then once that parent's task is complete, I'll know which of these subtasks I actually needed to run, take the results, and discard the remaining ones. Okay, you typically do this in the beginning, in the bootstrap stage of a program, where you don't have enough tasks. And so you say, I'll either sit, wait, do nothing, or I'll speculatively do something else, and if it gets used, great. It doesn't get used, I would anyway have been sitting idle. Okay, I've maybe burned some power. And then there are hybrid decomposition techniques where you do recursive somewhere, and then once you've got to a big enough task, then you do some more pipeline or some more domain decomposition at that point, and whatever. And the thing that you have to be, again, careful about is whether the tasks are known statically or they're being generated dynamically. Okay, and so now we have figured out what these tasks are. If they're static, then I start with a set. If they're dynamic, then I start with a small set with new tasks being generated as we get done with these old tasks. Okay. How do I decide which task to run where? That's the mapping problem. Mapping of the tasks. So the 2 stages are decompose and then map. Decompose into subtasks or tasks, if you will. Then map where to run this task. And typically you would not in fact, I've said that many times, you would not just have as many tasks as the number of processors you have live. Right? So if you have k processors, you will probably have 4 or 5k live tasks. Right? Which means you may in fact have many more tasks that you generate, such that 4 or 5k live ones can be kept at a time. Right? And once somebody has nothing more to do, you've got tasks waiting for him to start on. Okay? So you would generate, if you have P processors, well in 20, 30, 40 P tasks to begin with. Okay. Now you've got some 30 P tasks, P processors, and you're going to begin with some 4 or 5 P of them from the 20 P. So which 4 or 5 P should be done first? Because you want to keep that many live. You want to keep several tasks per processor live. And you want to keep some waiting so that once a task gets done, you can replace it with another. And so if you've got that many extra tasks and you have to choose a set which you want to start running, and that set also has to be grouped into P groups, then you've got it's an optimization problem to solve. From the big set of about, let's say, some number 20P, I'm going to choose 5P, and from the set 5P, I'm going to break it into P groups. Okay. What are the parameters? What would you be looking at? You want a group such that it does a lot of data communication. If two tasks share a lot of data, then they should be in the same group. And they should probably be launched together. Okay, so communication at this point, you look at the task interaction graph, and you will get a sense of which are the tasks that will interact with each other much more than others. You club them together onto the same processor. Again, the task mapping is easier if you know the size of the tasks, because then you can load balance if you know how many tasks there are. If it turns into a dynamic situation where tasks are being generated as you run them, some task runs and it spawns 4 new tasks, then it becomes extremely hard to properly map them. There have been results in specific types of mapping patterns, or rather communication patterns, right? And which are often found in applications. Examples are grid communication, so you only communicate with 2 or 3 neighbors of you, or some kind of restricted graph communication, or communication where I only read your stuff but never write another thing, or write something to you. Right? We are both reading some common shared data. So in these restricted environments, people have worked out mapping algorithms that work well. We are not going to get into detail of these techniques, but if you are interested, because again, it will work only for a very restricted set of environments. But if you're interested, you can look up these papers separately. The mapping itself is, as was pointed out, knapsack problem, which you've got to figure out somehow with some heuristics to arrange. And again, for restricted types of, this is related to the previous slide. If there are restricted types of communication patterns as well as dependency patterns, then you can do mapping using those specific patterns, especially if these patterns are data dependencies. Right? For example, you say, I have a task decomposition that is a domain decomposition based, and I've got a 2D array of data that we are going to all be processing. Then I'll simply do block decomposition. I'll take this block, you take this block, I'll take this block, and that all the threads of that block become mapped together. Okay, and then there are various refinements over block decomposition, where you say instead of, in some situations you may not want the entire block to be together because communication patterns across blocks are high, and then you turn it into cyclic blocks. You say I'll take one block, you take another block, third person takes third block, then I'll take the next block again. So instead of having the entire thing broken into P blocks where each block is then subdivided into the tasks, you break it into a fixed size block, but then cycle through the blocks. First block goes to first processor, second block goes to second processor, and so on. You can also do it based on, only for the static case, based on the task dependence graph also. You take the task dependence graph and you simply cut it into as many processors at k times that processors. If I wanted to break it into 5p tasks or 20p tasks, you create 20p subgraphs such that the edges that go from a subgraph to another subgraph are minimized, or the weights of edges. This also has a weighted version where some dependencies are given higher weight because they either communicate a lot of data or synchronize more often or whatever. And so it becomes a graph cut problem. You've given this dependency graph and you're going to cut some edges such that k subgraphs are generated. And you want to cut the most number of edges. For dynamic task mapping, you have essentially one category or with let's say two specializations of algorithm, where I've got essentially a group of tasks maintained in a queue and the tasks are being allocated to whoever has finished. This approach works reasonably well even if you have static tasks. Although the overhead of managing this queue is something that you can avoid if you don't do this work queue based optimization. And so the two specializations is centralized versus distributed, where there is a central queue somewhere and everybody says, I'm done, give me one task from the queue. So there's some synchronization involved and I'm going to get a task and do that. And then somebody has to maintain this queue. So when I generate more tasks, they must get added to that central queue in the dynamic context. Okay. The other variant is distributed, where you say everybody is initially allocated some task and they are dynamically generating more potentially. And when I get done, I simply go steal somebody's task. Okay, it's called the work stealing algorithm. And this is supposed to be one of the best techniques for load balancing. Okay. Again, there are details in terms of whose work should I steal, and how should I check, in which order should I check whether I should steal his work or not. And when I decide that I checked with someone and there is a lot of work remaining there, how much of that work should I take on? Maybe there are others also waiting to take on some more work. So if I take all of the work, then others will have to steal from me. So there's more overhead. Okay. And so essentially the overheads are pair to pair. So I decide, and one common technique is just randomly. I simply say, let's see whether you have any tasks remaining. And if you have, then I'm going to take some fraction of your remaining tasks. Okay. Okay, so let me stop with that at this point. These are the high-level techniques. I've also got a few slides which I'm not going to go through, called General Programming Tips, which is essentially a summary in some ways of the stuff we have talked about. There are 2 or 3 slides.
These are specific to MPA.
No, these are just general parallel programming tips that you need to keep in mind. No. Everything we are talking about today is not about OpenMP or MPI, but about parallel programming in general.
So you gave some more tips previous class. That was specific to MPA.
No, that was also. Right? And here those are encapsulated. So there are 3 slides here, tips 1, 2 and 3. And it will be posted on the website. You just review that. I will repeat one more time that it's, at least in the beginning, when you're not an experienced parallel programmer, focus on correctness before you focus on performance. Otherwise, you're going to spend a lot of time debugging, and debugging support in parallel context is not that great. Right? So printf is your debugging for most part. And so it's very important that you take conservative decisions first and then gradually improve the performance as you might. Any questions? I'll just flash these one after another in case you want to have ask a question right now. Alternatively, you can ask any question that you may have next class also. Don't use a lot of, this is again something that is generally a reasonable advice for sequential programs also, but even more for parallel. Don't use a lot of new or malloc and free type stuff. You don't want your memory to become fragmented in the sense of the threads working set. You want the threads working set to be contiguous as much as possible.
So while doing the first assignment, it was found that when I do malloc or new in parallel, it's slower than doing it in sequential, just the allocation part. So is it based on the architecture or?
No, it is not based on architecture. Use thread-safe library. Thread-safe libraries are libraries that somebody has built for you, which works even when multiple threads are calling that function.
So
malloc and new in the thread context takes more time because it is thread safe.
It takes more time.
Yes.
So we want to avoid thread safe.
No. Correctness before performance. They take more time because they are thread safe, but they're thread safe meaning that even in the context of thread, they are guaranteed to give you correct results.
So there are no libraries which give correct results and are nicely parallelizable.
There may be, right? But there is a cost to be paid for being thread safe, and that cost is what you are seeing. Any other question?
Keep a log, means multiple threads are system, so that would take time.
Okay, in that case, I'm going to stop here.